All right, welcome back. So let's talk about particle motion. We have a particle that initial position is zero. Excuse me, S of zero is zero. And its velocity can be represented by the equation velocity is equal to t squared for any time greater than zero. So I'm going to draw a quick graph of the velocity versus time. And we want to know the position of this particle at 3 seconds. Well, one thing I can do is I can divide this into strips. And I'm going to divide this into 12 strips of width delta t. So in this case, my change in time for each strip, because they're going to be of constant width, is 3 divided by 12, which is 1/4 of a second per strip. So let's zoom in on one of these strips. Let's zoom right in on just one strip and see what it looks like. Well, here's our one strip. With a width of 1/4 and a height, if I assume that the height of the strip is at the middle of that strip, but either way, the height of this strip is equal to some time squared. So if I call this t sub I, some strip, the height of this will be t sub I squared. Well, this means that the area of my strip will be base times height. So let's take a look at our subintervals. Oops, sorry, bumped the camera there. Let's take a look at our subintervals. Let's make a chart. My first subinterval is going to go from 0 to 1/4. My second is going to go from 1/4 to 1/2. My third is going to go from 1/2 to 3/4, 3/4 to 1, 3/4 to 1, and so on. And my final strip will be at 2 3/4 to 3. So where is the midpoint? The midpoint of each strip, because that's what I'm going to use for the height of the strip, is at 1/8. It's at 3/8. It's at 5/8. It's at 7/8. Hopefully we are seeing a pattern here. All the odd number eights. And so my height, and let's call this midpoint m sub I. So this is the first midpoint, m sub 1, m sub 2, m sub 3, m sub 4. Just an easy way to keep track of what I'm doing. And so the height of the midpoint, h sub I, will just be equal to that midpoint value squared. So I have a height of 1/8 squared, a height of 3/8 squared, a height of 5/8 squared, a height of 7/8 squared, and so on all the way up to the end of my region. Now let me just make sure we're able to visualize this. Here's my curve, and here's my first interval. So there's 1/4. And if I draw this rectangle looks like this. It has a height of 1/8 squared, and it has a width of 1/4, which means that the area of this little rectangle, my first rectangle, is 1/4 times that midpoint squared, which is 1/4 times 1/8 squared, and so on. So how do I find the total area? Well, the total area will be the sum of all my areas This equals 1/4 times 1/8 squared plus 1/4 times 3/8 squared plus 1/4 times 5/8 squared plus all the way to my 12th. Now, let's shortcut this a little bit. We can factor out the 1/4. We can factor out the 1/8 squared. And we're left with 1 squared plus 3 squared plus 5 squared plus ... And we're going to have 12 of these numbers, so that takes us all the way to 23 squared. And we get approximately 8.98 units. So what's the interpretation of this answer? The distance the particle traveled in the first 3 seconds was approximately 8.98 units. All right, we'll come back with another example. Thanks for watching. I hope you learned something.